So, first thing we want to really address is this idea of a closed system. What is a closed system? It's really important in this topic of thermodynamics because all the systems that we're talking about are going to be closed systems. So rather than something that's open and everything can escape and there's like loads of things there, we're talking about essentially something that's inside a box. Okay? So if you do a quick Google search, the first thing that comes up on Wikipedia is this. So there's just a few things I really want to point out. It's a physical system. So we're actually talking about reactions and what the ones that are happening. So we're talking about sort of maybe beakers in like on the table, etc. However, we're talking about beakers on the table which have lids on. So we cannot have a transfer of mass into and out of the system. So if we put a beaker and we seal it over the top, we can't add anything else in there. But other certain things can be transferred in and out. So in a closed system, we can have the exchange of energy. Okay? So I think someone said temperature going in and out. Temperature is a form of energy, so we can increase and decrease the energy. It's just we cannot change, or the total mass of the system does not change. But temperature can increase and decrease. So, energy can be transferred in and out. Oh, there we go. So, closed system in chemistry, energy enters and leaves freely. So it can go into the system and back out the surroundings, out the system into the surroundings, etc. But mass does not change. If we can exchange both energy and matter, so say we took the lid off and the gas was escaping, then that would be an open system. So literally, I just think of it really as a beaker on the table. I'm there putting my hands on the table as I'm holding a beaker. But a beaker on the table or like a glass of something, if it's open, things can escape. If it's closed, it is sealed and not everything inside cannot escape. But we could still heat it up externally. Okay? Now, other ideas, concepts that we need to maybe think about, like what's actually happening during a reaction. And again, we're just going to touch and refresh on some of the GCSE style stuff at the minute. So if we just take the combustion of hydrogen in oxygen, we're going to combine them together to make water. But in order for that to happen, hydrogen is H2, oxygen is O2, and water is H2O. What we're going to have to do is we're going to have to break the bonds between the hydrogen atoms, like in the hydrogen molecules, and break the bonds between the oxygens, and then remake new bonds in the water. So we're breaking HH bonds, OO double bond, and we're remaking bonds, oxygen and hydrogen. And this is kind of what we're representing with our equation. We're representing the breaking and making of bonds. This okay. This happens if you think about just something to do with kinetics, which we'll do in a later topic, but again, it's recapping energy. But molecules collide, and they need to collide first, they need to bang into each other with a certain amount of energy. And we call that the activation energy, EA, energy of activation. If they collide with an energy that's greater than that, what it allows us to do is it allows us to break the bonds between the molecules, or between the atoms, and that requires energy. It takes energy in. It's an endothermic process. And then we get to remake new bonds. And making new bonds is exothermic. It releases energy. This whole topic, what we're looking at the balance between making bonds and breaking bonds, and which one requires more energy and which one gives out or takes in more or less energy. And it's the balance between the two. If it requires more energy to break them than it does than is given out, we end up with an endothermic process. If it gives out more energy when it's making new bonds than it requires to break them, we have an exothermic process. Okay? So if we look at an exothermic energy diagram, we're just putting an arbitrary scale up the side here, and from left to right is, well, we tend not to label it, but it's essentially time. We have our reactants. These are at a specific energy level. We can't say what energy level they're at because we can only measure changes between them, like the difference, which is why we use an arbitrary scale. We're saying that it requires so much energy to break them, and that putting energy in means that we end up with like a transition state or something in the middle, something that doesn't actually exist, but where all of the reactants bonds are broken. And we call this an intermediate, and it's very difficult to isolate these, get them themselves. But then the intermediates reform, making new bonds, which is an exothermic process, and give us our reactants, our products. So, making bonds or breaking bonds, energy in, making bonds, energy out. This energy difference between the reactants and the intermediate, where we're breaking all the bonds, is essentially our activation energy. How much energy it needs in order to start the reaction happening. Okay? The difference between our reactants and our products, that's the overall energy change in the reaction, is known as our enthalpy change. And this has come up a little bit strange. Really, that symbol there, I thought I'd change them all. But it is a delta, the Greek delta, which is just a triangle. Okay, so just a triangle, delta, and it means change in. It's the difference between this one and this one. And for an exothermic process, the energy change is negative because the products are lower in energy relative to the reactants. Okay? Good, activation energy. You, as part of your notes, should also draw an energy diagram for an endothermic process. So I've drawn one here for an exo. I'm expecting you in your notes to put in one for an endothermic process as well. And be able to label all the different points and state what the different labels are. Again, this is just an extension of GCSE. Those of you that did double, probably it's new stuff. Okay? So the enthalpy change of a system the heat energy change, the temperature or the change in energy that happens at constant pressure. What we do is we say here that the enthalpy change, and we put this little symbol here, which is like a circle with a line through it, and that tells us that it's under standard conditions. Sorry, this one here is supposed to have a line through as well. So circle with a line. And we're saying that it's at a temperature of 298 degrees Kelvin, which is 25 degrees Celsius, and a pressure of 100 kilopascals, which is 1 atmosphere. So room temperature and atmospheric pressure. And by definition, the activation energy is the minimum energy needed to break the bonds and start a reaction. Okay, I didn't want you to do that. Okay. Now, those are the basic principles that I'd like you to sort of cover. The other thing that I'd like you to cover is this experimental type thing. So I'm going to ask you to write out a method for how we would actually find out the enthalpy change empirically. Like, how would you do it through experimentation rather than theoretically? We're going to look in later lessons at looking at bond enthalpies. Again, this will be familiar to triples, but maybe not to doubles. But we're going to look at bond enthalpies and working it out theoretically. But here we're going to work it out empirically through experimentation. How could you do it? And you'll have all done this experiment, I think, where you take a fuel and you heat up some water and you measure the temperature change. You know the mass of the water, you know the mass of the fuel that you've used, and you can measure the temperature. So what we can do is we can use the specific heat capacity of water. Okay, notice that now we're in per Kelvin and our temperature is measured in Kelvin rather than in degrees C. We just had 298, but it's the same as the difference in degrees C. Q is our energy change and it's measured in joules. This is important. Joules. Mass is the mass of the water, not of the fuel. We're measuring the temperature change of the water. Specific heat capacity is how much energy there is inside those water molecules, or how much it can actually hold. Yeah? This is a definition. This is probably something that you should get down in your notes as well. Okay, and this is just a standard thing, which again is in your data booklet. So we have an energy change, but I've asked you to calculate an enthalpy change. So what's the difference between energy and enthalpy? Well, enthalpy is the energy change per mole. So we can use the specific heat capacity to calculate the energy change, but then we need to know how many moles of fuel we've used. So it's the moles of fuel. And we can just do this simply by taking the mass of the fuel divided by the MR of the fuel, and that should give us the number of moles. Then it allows us to work out the enthalpy. Remember, our energy change per mole. Notice as well that this is measured in kilojoules per mole. Okay? Our energy change that we worked out before, using specific heat capacity, is measured in joules. We need, for an enthalpy change, to change it into kilojoules. Mm-hmm. So we need to divide by 1,000. And it's as simple as taking our energy change and dividing by the number of moles and then converting the units. Okay? Other things. Enthalpy changes are vector quantities. They either go up or they go down. Okay? We either have an endothermic or an exothermic reaction. So you need to put a sign in there. We can put a sign based on whether, like empirically, observation, whether the reaction is endothermic or exothermic. Either or, our energy change here will be, because it's an increase in temperature, there'll be a negative enthalpy. If it was a decrease in temperature, we would have a positive enthalpy change. So I want you to write out the experiment, like the method for this. I'd also like you to explain the different stages in the calculations. Like you need to do this, you need to do that, then you need to do this. And why you need to do each stage. I told you I'd talk for ages. The final thing is covered on this slide, and you should have this slide here. So there are loads of problems with this experiment. You can see them highlighted here. We covered them at GCSE as well. So here, there's loads and loads of problems. There's loads of assumptions that we are making. And also there's loads of things to do with the energy transfer. We're assuming that chemical goes to heat that goes directly into the water. But there's loads that's lost. So you need to identify what all the problems are with this experiment. Like, what are the issues? So what are the problems? Say how it would affect the value. So it's almost like an evaluation. And then I need you to look at a bomb calorimeter. In the background is a bomb calorimeter. And I want you to say what it is and how it addresses all these different problems. Okay?